Okay, we're going to talk about how we get from grass to milk via the cow, and we're going to try to draw this out um, sort of like we described on Tuesday, but this is for the people that couldn't make the lecture. We're kind of repeating it. So, milk components, where do they come from? We've got water, lactose, fat, protein, minerals, and vitamins. So this is the diagram we presented on Tuesday. This is kind of the abbreviated version. So here's what's in our grass. We've got neutral detergent fiber, carbohydrate, water, glucose and starch, protein, minerals, vitamins. They're all going to go in the rumen. There's a fermentation going on there. What comes out of the fermentation is bugs, and then we've got products. So water is going to kind of bypass through the system unchanged. So that'll be going through the blood in the liver, back to the heart. You've got from the fermentation, you've got acetate, propionate, butyrate, 2 carbons, 3 carbons, 4 carbons. You've got microbial amino acids coming out of the fermentation, the microbes, the bacteria, the protozoa, the fungi, all become sources of amino acids for the cow. We've got feed amino acids um, that aren't touched in there. We've got starches coming through, minerals and vitamins. We've also got some waste products that are of no use to the cow, the heat, carbon dioxide, methane, water are also end products of fermentation. The heat is only useful in the wintertime. It's a problem in the summer. So water is going to be drawn in by the osmotically active particles, the solutes that are produced in the milk, the main one being lactose. So water is going to follow lactose passively as it goes through the body. It's going to be drawn out of the blood and into the milk. Fats, we're going to have fats. Half of the fat in the milk is either transferred from another part of the body, so either absorbed in the diet, transferred out of the blood, taken off her back from her adipose tissue. That's going to account for about 50% of the milk fat. The other 50% is going to be made in the udder. So you're going to make glycerol from the glucose that might be absorbed, gluconeogenesis. So we've got lactic acid, propionic acid, used gluconeogenesis. It's going to create a glucose pool in the blood. Some of that is going to be used here to make glycerol in our fatty acids or triglycerides. And then we'll take acetate, string them together 2 at a time, and make fatty acids. The glycerol and the fatty acids stuck together, and they are half or 50% of the milk fat that's put out. Protein, that's going to come from our absorbed amino acids as building blocks. We can have stored amino acids. So if a cow is losing condition, she's going to lose both fat and protein off her back from her muscles. Those stored amino acids might be part of the pool that the udder uses to make protein. We also know the liver can synthesize amino acids. So 4 sources of amino acids ending up the udder: microbial absorbed protein, feed absorbed protein, the fatty acids off her back from her muscles, or the fatty acids created in the liver will all provide the amino acids to build the protein. Again, we're using blue here to denote a process, so making protein, making fats, bringing in water. Lactose is going to be created in the udder, whereas fat and protein are variable across our breeds of cows. So fats anywhere from 2% to 6-8%, depending on where we are. protein 3 to 4 or 5, depending on that. Lactose is going to be fairly constant. So 3.8% of milk is lactose. So if you got a cow producing 100 pounds of milk, that's almost 5 pounds of lactose every day is generated in the udder. So we take 2 6-carbon units from our glucose pool. We're going to generate lactose. We have a glucose and a galactose. So the glucose is absorbed. That's ready for one half of the molecule. We have the other glucose is absorbed and isomerized, rearranged to make galactose. The glucose and the galactose are stuck together. They're going to make the lactose. The lactose is secreted into the lumen of the alveolus in the udder. That is a solute in solution. It's going to draw water in to the milk. So you have water going down its concentration gradient to the milk. Minerals and vitamins are absorbed at the small intestine. They go through the liver largely unchanged. Minerals are constant. They're going to pass through the body and be absorbed by the other, passed on to the milk. The vitamins, either from the diet or created in the rumen, are going to be absorbed. Some A and D and E might be stored in the liver. The B is certainly going to pass out very quickly to the rest of the body. Are water soluble vitamins, but they're created either by the plants in the diet or by the microbes. They're going to be absorbed into the liver and pass unchanged into the vitamins of the milk. So that's kind of an abbreviated look. This is good for figuring out, okay, what ends up where. So where does propionate go? Where does butyrate go? Here we got a dotted line that sometimes we got some butyrate absorbed, not burned by the wall of the rumen. It can be used to make fats as well. So even numbers are used to make fat. Odd is used to make carbohydrates, specifically glucose. This is a more schematic one I've developed for this year. Again, we have our black is our pathways, green is our nutrients, our blue ink is processes in some way, shape, or form. So we've got our end products of digestion and fermentation. Acetate's going to be absorbed, propionate, butyrate's going to be mostly burned by the walls of the digestive tract. We've got protein, we've got feed protein there. We're going to focus on the things that are synthesized. Water passes through unchanged, minerals pass through unchanged, vitamins pass through unchanged. We have synthetic processes here in the mammary gland to generate these three components. So if we start with protein, we have microbial protein going into the small intestine, digested, hydrolyzed into amino acids. The amino acids are absorbed. You have the amino acid pool in the liver coming from microbial source, feed source, and then synthesis in the udder. Those amino acids are released into blood. We can also have the muscles releasing or taking up amino acids either way. So synthesis and degradation will contribute or subtract from the amino acid pool. We have protein synthesis in the udder. That protein is secreted into the milk and becomes part of the mixture that we enjoy, or at least I enjoy so much. Lactose, the primary function or primary builder of lactose is going to be propionate. So we've got a 3-carbon unit. We take 2 3-carbon units, we run them through gluconeogenesis. That's going to create glucose. That happens in the liver. That's a main function of liver in our dairy cows to generate that. If there's a cow with 100 pounds, almost 5 pounds of sugar, that 5 pounds of sugar has got to be generated in the liver. So we need healthy liver function. That glucose passes to the blood. It's extracted by the mammary gland. We have the glucose stays as is. We rearrange another glucose. We make galactose. You stick those two together, and then you have lactose synthesis. Lactose is secreted into the lumen of the alveolus to form milk. Fat is the most complicated of these three components. Again, we said 50% transfer from pre-existing uh, situations. So you have from the diet or off her back. We have fat being transferred in. About 50% of the dairy cow's fat comes from those sources, pre-made transfer. So the mammary gland extracts it from the blood and just moves it over into the milk. Or we can create fat from acetate and glucose. Glucose is going to make our glycerol, so we run glycolysis basically to get pyruvate. Pyruvate, the three carbon atoms are converted to glycerol, another form of three carbon atoms. And then we have the acetate is going to be used to generate the fatty acids. So two at a time. Propionate, butyrate might also be involved in there. So acetate, butyrate, the even numbered 2 and 4 are used to make fatty acids. Those fatty acids are stuck to the glycerol, and that generates the triglyceride that is part of the milk fat. So here's a diagram we did last 2 years ago. A little bit different presentation, but the same net effect. Again, we've got everything here. In the last slide, we focused just on these three. A little bit more discussion here about breaking things down, digestion, what ends up where. We're going to focus on absorption. Here's everything in the liver. What leaves the liver goes to the heart, goes to the muscle, goes in the amino acids, go in the muscle, come out of the muscle. We've got pre-made fat, acetate, and glucose going into adipose. We've got storage and synthesis of triglycerides. Triglycerides can be exported and they go back to the heart and they can end up as part of the pre-made fat. So we have the blood right here in this column. The blood has all the components, the building blocks. So inputs are building blocks from the blood, the processes that occur. So we just have transport of vitamins, transport of minerals. Water follows the lactose passively. We have synthesis and transfer of fats to generate our milk fat. We have protein synthesis to generate protein. Take our amino acids, string them together. We have our proteins. We take two glucoses, we make lactose, and these are the ranges associated with milk. So it's slightly different presentation, a little bit more robust perhaps, also a little bit more confusing than the one I just generated for this coronavirus year. So again, we want to focus on where does acetate go, where does propionate go, where does butyrate go, where do the amino acids go. So how do we follow them through these various outlines? How do you get from the components in the rumen, the fermentation in the small intestines, to the components of milk? Can you trace the pathway? These are the things we're going to talk about in our reviews on Tuesday and um, possibly Wednesday if you need it before we give you the exam at the end of next week or the Thursday of next week, or maybe Wednesday, depending on what you guys want. So how do we get from propionate in the rumen to fat in the milk? How do we get from propionate in the rumen to lactose in milk? How do we get acetate in the rumen to fat in the milk? How do we take NDF or cellulose in the rumen? And how does that become amino acids in the casein in milk? How do we take the cellulose, the NDF in the rumen, to the amino acids in the myosin complex in the muscle? How do we get propionate in the rumen to protein in the milk? How do we get from cellulose in the rumen to fat in the milk? And there are a couple different pathways given the VFAs that are produced by fermenting that cellulose, that NDF. So, how do we get from a specific input building block to a specific output? How do we get that done? Then, thinking about the building blocks, if we're looking at the end product focus, where do the building blocks from protein come from? What are they? Where do they come from? Where do the building blocks from lactose come from? Where's the primary source of those? Where do we get the building blocks for the milk fat that the cow puts out? So, looking at those three layers, those are the questions that'll be on the homework. You'll have an opportunity to work those, but you should be able to take those diagrams and trace through how it all works. Here's an example. What happens to glucose in the body? So you have glucose in the small intestine, glucose in the liver. You can have it glycolysis. If there's no oxygen, it generates lactic acid, like we saw in the muscle. We can take that lactic acid and regenerate it with gluconeogenesis. So glucose becomes two lactic acids. Two lactic acids can circle around and go there. So you're going to take glucose, you're going to take two of them, you're going to generate milk lactose. You're going to take hundreds of them, you're going to generate glycogen, our storage form of glucose in the body, either in the liver or the muscle. You break apart glycogen with glycogenolysis, that's going to generate your glucose pool again. You can take those carbons and we use them to create or repurpose them for our generic amino acid, and we can use it to generate non-essential amino acids, which will end up in proteins. So that glucose can end up in protein. Glucose, we can usually generate triglycerides. We focus on taking the glucose, breaking it down to 3 carbon units, glycerol. But if we got a whole lot of extra in a human body or a pig, that glucose could be used to generate fatty acid chains. That's not usually what happens in our dairy cattle, but sometimes they can do that. We focus on the acetate to make our fatty acid chains. So glucose making that some way, shape, or form. So that's an example of where does glucose go. So that's one way to take an input and trace all the different pathways that it might go.